Hello, right, let us help you with some physics here. This is Combined Science Paper 3, which basically means it's Physics Paper 1, and it's the higher tier. You'll get 1 hour and 10 minutes, and the test is worth 60 marks. And this is the 2020 paper. Right, question 1. A student lifts a toy car from a bench and places the toy car at the top of a slope as shown in figure 1. Part A. Describe an energy transfer that occurs when the student lifts the toy car from the bench and places the toy car at the top of the slope. Right, well, the student has got chemical energy. And if they're moving the car, it's going to get turned into kinetic energy. And then when it's at the top of the slope, it's going to have gravitational potential energy. So that'll get you your 2 marks for that. Part B. The student lets the toy car roll down the slope. Describe how the student could find by experiment the speed of the toy car at the bottom of the slope. Right, base your explanation on the calculation. So speed equals distance over time. So we're going to need to measure a relevant distance, measure a relevant time, and then do the calculation. So if we say we'll measure the distance at the bottom of the slope, tell them with what? So with a ruler. That's the detail, and measure the time with a stopwatch. And then calculate speed using that equation. So as I say to my students, always base your explanation on the calculation, and then it's easy. Part C. The student needs to develop the experiment to determine the loss in potential energy and the gain in kinetic energy as the toy car is rolling down the slope. State the other measurements the student must make. Well, once again, base your explanation on the calculation. So if they're going to get the gravitational potential energy, they're going to need the mass, gravity, and the height. And if they're going to get kinetic energy, they're going to need the mass and the velocity. Right, well, squared. Now they've already got the velocity. That's basically the speed. So we're going to need to measure the mass and the height. And that's where you'll get your 2 marks from. Part D. When the toy car rolls down the slope, some energy is transferred to the surroundings as thermal energy. State how the student could calculate the amount of energy transferred to the surroundings. Right, if we go back to the original setup, right, the gravitational potential energy that the car has at the top should equal the kinetic energy at the bottom. However, what they're saying is that some kinetic energy is going to get lost. So just say this here is like 400 joules and this here is 300. Well, you can tell that we've lost 100. And the formula that we would do is if we take the GPE and we take away the kinetic energy from it. So if we say gravitational potential energy, take away the kinetic energy, that will tell us the wasted energy that got transferred to the surroundings. Is that all right? Question 2a. Which of these is a vector? So a vector has size and direction. Energy, no. Force, yes. Mass, no. Work, no. Part B1. State the equation that relates acceleration to change in velocity and time taken. Right, acceleration equals change in velocity divided by time taken. Part 2. A van accelerates from a velocity of 2 meters per second to a velocity of 20 meters a second. Right, so that's the velocity u at the start and that's velocity v at the end. So change in velocity, that's basically v minus u over t. That's the way you can see it. So that's the final velocity and that is the initial velocity. And they're doing that in 12 seconds, so that's t. Calculate the acceleration of the van, so a is our target, so we'll just do a equals v minus u over t, pop the numbers in, so that's 20 meters per second, take away 2 meters per second and divide that by 12 seconds, and that's 1.5 meters per second squared. Part C. Figure 2 is a velocity time graph for 15 seconds of a cyclist's journey. Calculate the distance the cyclist travels in the 15 seconds. So distance travelled on a velocity time graph is the area under the graph. So all of this bit here. So you can see that's a triangle and the area of a triangle is a half times by the base times by the height. So the base is 15 seconds and the height is 7 meters per second. And that equals 52.5 meters. The area under the graph isn't always a triangle. Sometimes it might be a rectangle, in which case you just do the height times by the base. Another cyclist starts from rest, but his acceleration decreases as time increases. Sketch the velocity time graph for this cyclist on figure 2. Okay, so the gradient of a velocity time graph is acceleration. He starts from rest, so that means at time 0 it's going to be a velocity of 0, and the acceleration decreases as time increases, so that means it's going to start off steep and then get not as steep. So it's going to start off steep just like that, and then it's going to be not as steep. If you analyse the gradient, it's a steep gradient at first, which means it's a big acceleration, and then it's not as steep as we get towards the end, which means the acceleration has decreased. Question 3. A radio station transmits on 97.4 megahertz, so that's the frequency. And if it's megahertz, that's times 10 to the 6. To receive the waves, an aerial needs a length equal to half the wavelength of the radio waves being transmitted. Calculate the length of the aerial needed. The speed of the radio waves is that. Right, so we've got speed of a wave is your frequency times by the wavelength. So therefore The wavelength is going to be the speed divided by the frequency. So if we put the speed in, divided by the frequency, that'll tell us the wavelength, and that comes out as 3.08 meters. Now remember, the aerial needs to be half of the wavelength. So if we do 3.08 divided by 2, that'll tell us the length of the aerial needed. So that's 1.54 meters. Part B. To investigate refraction in a rectangular glass block, a student uses the apparatus shown in figure 3. Describe how the student should measure the angle of refraction. Now it's only worth 2 marks, but this answer I'm going to give you is probably going to be worth 4. Right, they're going to need to draw around the glass block. Now where the light goes in, if they draw 3 crosses along where the light goes in, and then if they draw 3 crosses where the light comes out, then they're going to need to move the glass block. That's why they've drew around the glass block. Right, then you'll have your little normal in like that. Then you'll take a ruler and draw a straight line there, and take a ruler and draw a straight line there, and then you'll have to connect that to that. If you're going to measure the angle of refraction, that's this angle here, R. And that is the angle between the refracted ray and the normal. Now, how we're going to say that? Like I say, this is probably worth more than 2 marks. Now I'm looking at the mark scheme when I'm going over these papers just to make sure I'm hitting everything. It could be a bit risky just to say that and that, but technically that's all you need to say for the 2 marks. But on the mark scheme it does actually give a bit more detail like that. Now if you remember this process, this could actually get you 1, 2, 3, 4, 5, 6 marks. So I would just try to memorise this process. That's why I've annotated this diagram here and basically talk you through the question. What they also sometimes say is tell us how you'd measure the angle of incidence. Well, that's it there. It's in between the incident ray and the normal. And remember that ray there is called the refracted ray. Okay, hope that's helpful. Question C. Figure 4 is a simplified diagram to show radio waves from a transmitter moving upwards, then meeting the boundary between lower and upper layers of the atmosphere. So that's going up there. Some of it goes into the upper layer and some of it reflects off the boundary. Explain what happens to the radio wave when they meet the boundary between the lower and upper layers, as shown in figure 4. Your explanation should refer to changes in direction and speed of the waves. Right, technically this line here is the normal, so it should be dotty. I don't know if they've done it a straight line to try to confuse you, but keep an eye on any rays because they've got the arrows on. Right, now when I'm teaching my students, I use the acronym FAST. If the wave gets faster as it crosses the boundary, it's going to move away from the normal. And if the wave goes slower as it crosses the boundary, it's going to move toward the normal. Now we can see that ray P moves toward the normal. All right, instead of shooting off over here, it's actually bending in and moving toward the normal. That angle there is smaller than that angle there. So if it moves toward, that's because it must be going slower. So we'll talk about rate P first. That's 2 marks. And then obviously Q is reflecting off the upper atmosphere. And there'd be no change of speed for Q, because it's still travelling in the lower layer, so it hasn't changed density. Remember, if there's a change of density, there'll be a change of speed, and then there'll be a change of direction, unless it's entered along the normal. Question 4. 4 students and their teacher do an experiment to measure the speed of sound in air. The teacher stands at a distance and fires a starting pistol into the air. The students see the flash when the pistol is fired. They measure the time from when they see the flash to when they hear the bang. A student drew a diagram of the arrangement as shown in figure 5. The students obtained a value of 240 meters a second for the speed of sound. The accepted value in a science data book is 343 meters a second. Calculate the difference between the student's value and the accepted value as a percentage of the accepted value. Now this is standard stuff at A-level physics, which I taught for 20 years. I'm not sure how standard it is at GCSE though. Right, your percentage difference equals your value minus the accepted value divided by the accepted value. So their value was 240. The accepted value is 343. We need to divide that by the accepted value. And that comes out as minus 0.3. Now, because they want it as a percentage, we do need to multiply the whole thing by 100. So that's minus 30%. Point 0. Part 2. When the distance was 100 metres, the students measured the following times. Explain why their times vary so much. Right, well, it's human reactions, so some humans might have better human reactions than others. On average, the human reactions are a quarter of a second, but everybody's different. Look at where the people are standing. Some people are closer and some people are further away. So that could be an influence as well. Part 3. Explain one way the students might improve this experiment. Right, they're standing too close to the teacher. If that's the time, 0.43, they're standing far too close to the teacher. If they moved another few hundred metres away, that would give them more time to start the stopwatch and then to stop the stopwatch. So these times here are what we call comparable. They're about the same size as the human reaction time, which is a quarter of a second. So that's what the problem is. So increase the distance from the teacher to the pupils so it's easier to operate the stopwatch. Or you could literally say, get a computer to do the measurements for you, so then that negates human reaction time. Part B. Figure 6 represents a sound wave coming from a loudspeaker and shows the effects on particles of the air at one instant in time. Draw and label a distance of one wavelength in figure 6. Right, you can sort of see there's a compression there, so that would be one wavefront. And then there's another one there and another one there. So a wavelength is basically from one wavefront to the next wavefront. So that's your wavelength there. Or it could be that there, and it should be that there. So they're all roughly the same. Part 2. Draw the motion of the particles as the wave travels through the air. So it's sound, which is longitudinal. So let the examiner know that you know it's longitudinal. And if the wave is travelling that way, then the direction of the vibrations is backwards and forwards, which is parallel. Question 5. Which of these describes isotopes of an element? So it's got the same number of protons, or atomic number, but a different number of neutrons. Right. Same atomic number, different number of neutrons. There you go. A. That question's usually worth 2. Part B. Figure 7 represents a decay that can happen inside the nucleus of an atom. Which decay is represented in figure 7? So we've started with a proton, which has got a mass of 1 and a charge of +1, and we're ending up with a neutron, which has got a mass of 1 and a charge of 0. Right, what goes in must come out. So we've accounted for the mass. This is what we've got at the start. So, and this is what we've got at the end. So the mass has been accounted for, but the charge hasn't. So this mass must be negligible. And the charge must be +1. So what has got like next to no mass and a +1, that's beta positive. So beta plus. Question C. The half-life of cobalt-60 is 5 years. A school cobalt source has an activity of 38.5 kilobecquerels in the year 2000. Estimate the activity of this source in the year 2020. Right, well, if the half-life is 5 years, that basically means it's going to be 4 half-lives. So we've got 38.5 kilobecquerels, that's the activity at first. 5 years later, it's going to half. And then 5 years later, it's going to half again. Another 5 years, it'll half again. And then another 5 years, it'll half again. So it's basically going to half 4 times. And that's exactly how I would set it out in your exam. And that comes out as 2.4. And because I just left it in kilobecquerels at the start, it'll be in kilobecquerels at the end. Why did I leave it in kilobecquerels? Well, I should have told you. I noticed that they wanted the answer in kilobecquerels, so that's always a good thing to look at the units. Half, half, half and half, that's the same as dividing by 16. But you could just type it into your calculator 4 times, just half it, half it, half it, half it. Question D. Explain what can happen to the body if a person has a prolonged exposure to gamma rays. Right, always the same answer. Can damage your cells and cause cancer. Simple as that. Question E. A Geiger molar tube is connected to a counter. A teacher places the GM tube next to a radioactive source. A student starts the counter and clock at the same time and writes down the readings shown on the counter every 15 seconds. The student plots the readings with a line of best fit as shown in figure 8. Part 1. Calculate the average count rate in counts per second from the graph. Show you're working on the graph. So once again, if we look at the units, they just want the counts divided by the seconds. Right, well that's the counts up the side and that's the seconds. So they're just basically wanting the gradient. And the gradient is a straight line, so we can just take any value from the count rate and divide it by its corresponding time. So if we just take something convenient like that point there, that's going to be 1200 divided by 82. And that'll equal 14.6. But with these type of questions, they will accept a range. For example, what if I took this value over here? I mean, what even is that? That's a right nightmare. I wouldn't take that. Here, do this one. 1,000. And we're dividing that by 68. That's just out of interest. 1,000 divided by 68. Yeah, that's 14.7. So that proves that because it's a straight line, you can pretty much take any value and its corresponding value. I wouldn't put loads of lines on the graph if I was you though. I've just done a few, just as an example. That's how I would leave it. Part 2. The student says that the experiment must have been done carelessly because the data seemed quite scattered away from the best fit line. The teacher claims such results should be expected in radioactivity experiments. Justify the teacher's claim. Right, well, radioactive decay is random, so the count rate will not be constant for each reading. The readings will vary. And that's your 2 marks there. Question 6a. Figure 9 is a diagram showing a rocket that is sent into space to try and change the path of a small asteroid. So firing the rocket at the asteroid. The rocket has got a mass of that many kilograms and it's travelling to the right at 14 kilometers per second. Which of these is a correct calculation of the momentum of the rocket in kilograms meters per second? And they even give you the equation. So just take the mass and multiply it by the velocity. Right, they're wanting it in kilograms meters per second, so we're going to have to convert that. So that's 14 times 10 to the 3 meters per second. So they've been a bit sly there. Just watch out for that one. And the answer comes out as 7.7 times 10 to the 9 kilograms meters per second. So the answer is C. Part 2. The asteroid has a momentum of 7.5 times 10 to the 10 kilograms meters a second and a mass of 8 times 10 to the 6 kilograms. Calculate the speed of the asteroid. Well, that should be velocity really, because that's velocity. It doesn't matter. Alright, so momentum equals mass times by velocity. So therefore we'll rearrange that to get the velocity. That's going to be the momentum over the mass. So just pop the numbers in. And that equals 9,375 meters per second. Part B. A student investigates the effect of a crumple zone on the force exerted during a collision. The student has one trolley with a spring at the front and another trolley without a spring. Okay, so this is rigid and this one is flexible on not rigid. The student uses the arrangement in figure 10, so they're just going to roll the trolley down and smack it into that rigid wall. After a trolley is released, it accelerates down a slope and bounces off a rigid wall. The speed of a trolley can be measured just before a collision with the wall and just after a collision with the wall. The silver foils are connected to a millisecond timer. The silver foils make contact with each other during the collision, so the time they are in contact can be read. Time they are in contact. Explain how the student could investigate the effect of a crumple zone on the average force exerted during the collision. I mean, this is a 6-mark. It's going to take 6 minutes to read the question. Your explanation should include how to determine the force. You may wish to refer to an equation from the list of equations at the end of the paper. Yep, base your explanation on the equation, definitely. How the effect of crumple zones may be shown in the investigation and precautions that may be necessary to achieve accurate results. Right, well, first things first, let's start with the equation. So impact force equals the change in momentum divided by the time taken for the change. Right, let's see if I can actually find that on the equation sheet for you. There. Force equals change in momentum divided by time. So that should really say impact force. Now the change in the momentum will be the momentum before, take away the momentum after, but I don't think we're going to need that because they haven't given us any values. So we don't need to do any calculations. Right, let's talk about the trolley with the spring first. Right, what's going to happen is with this spring, it's going to crumple on the front and that's going to make the time increase. Now, if the time increases, that means that the impact force is going to decrease. Now, imagine it's you, right? Let us try to explain this to you. If you jump off something and you land on the floor, and you keep your legs stiff, they're very rigid. Now, you're going to stop very, very quickly, and that's going to give you a big impact force. However, if when you land, you sort of bend your legs, that means that the impact force takes longer. The impact force will be smaller because your time's going to be bigger. Right, the trolley without the spring, the rigid trolley, the impact force will be bigger because the impact time is smaller. Alright, so basically the change in the momentum happens over a smaller amount of time. All right, and you can see over here the change in momentum would take longer. Okay, so there's the impact force, is the change in momentum over time. So that time is big, which makes the force go small. And for this one, the impact force, the change in momentum over time, this time is small, which makes the impact force big. Just imagine an airbag. An airbag is designed to make your impact force smaller because the time that it takes for your head to slow down is longer. Whereas if you're just hitting a rigid steering wheel, your body is going to stop very, very quickly. So you're going to have a big impact force on you. Now it says any precautions that may be necessary to achieve accurate results. Right, just pretty standard stuff. Repeat the experiment and take averages. And just make sure that you start the trolley from the same place each time. You could say the same pushing force, same angle of ramp. Right, so there's tons there, you'll easily get 6 marks. And finally, question C. Newton's third law, when applied to a collision of the rocket and the asteroid, as shown in figure 9, can be stated as follows. The force exerted by the rocket on the asteroid is equal and opposite to the force exerted by the asteroid on the rocket. Explain how this statement links to the conservation of momentum in the collision. Right, well, first things first, what is the conservation of momentum? Well, that basically means the momentum before the collision is going to equal the momentum after the collision. Right, so as we've just saw from the last question, the impact force on the rocket is going to equal the impact force on the asteroid, which means the change in momentum over time for the rocket is going to equal the asteroid change in momentum over time. Now, they did say that the impact force is going to be the same. So we can cancel it out. So therefore, momentum change is the same for both. And that should get you your 4 marks. So there we go. That's a bit of a stinker, that question. I have saw it a few times over the years. It's usually badly answered by students because it's quite tricky to remember all of this information. Right, well, that's the full paper. 60 marks done. Good luck with any exams that you're sitting, especially the GCSE exams on Thursday. Right, I'll try to do a couple of more videos before the next GCSE exam if there's a demand for it. Right, work hard, be nice, and bye for now.